All right, we're starting sections, 16.3, acid base strength and equilibrium law. You'll be using these notes mostly for your assignment 3.5. Okay, so we're just looking at basically taking what we've already learned about Kc, or like the equilibrium constant, and changing it so it's for an acid. So the equilibrium reactions for weak acids and bases are essentially the same as any other equilibrium reaction and can be treated mathematically in the same way. So the equilibrium constant, denoted as Ka instead of Kc, is just for the acid ionization constant. So we put an A there because it's for our acid ionization constant, okay, instead of the C, which just represents for any kind of constant. Okay, in your data booklet on pages 8 and 9, you have a bunch of different Ka's values for your different weak acids that are on there. Okay, the acid ionization constant. So by using the general formula of HA to represent any monoproduct weak acid, the equilibrium of the weak monoproduct acid can be written as this. So our weak acid plus water will produce hydronium plus the conjugate base of that weak acid. Okay. This is a heterogeneous equilibrium containing a pure liquid, which is water. Okay. We have to remember that pure liquids or pure solids, in any case, have constant concentrations. Okay, so we don't actually include them because their concentrations can't change. And so the equilibrium expression in general for any weak acid is Ka is going to be the concentration of hydronium times the concentration of your conjugate base divided by the initial concentration of our weak acid. So in weak acids, the number of acid molecules that ionizes is really small. So the position of the equilibrium in pretty much all cases lies really far to the left, which means like it'll have a really small Ka, like times 10 to the negative 5 or 6 or 7. Okay, so the concentration of acid, our initial acid here, our Ha, is larger than the concentration of our other ions, so our concentration of hydronium and conjugate base. So the Ka for weak acids are always very small numbers. The smaller the value, okay, the weaker the acid is, and very weak acids have a Ka value of less than 1 times 10 to the minus 15. Again, we talked about earlier that if it's less than minus 1 to the minus 10, then it really doesn't go in the forward direction at all. Okay, the Ka value of hydronium ion is also relatively large with weak acids. However, hydronium is still a weak acid. And so, like, yeah, if we look at the Ka value for hydronium, I believe it's right around 1. Okay, and so it's still considered a weak acid if it's just on its own. Okay, strong acids, okay, they ionize completely, so they go almost 100% to they go 100% to make their product. Okay, and so this would be an example of our strong acid. They're going to have really high Ka values, and that's why, like, it doesn't say them in the booklet, it just says really high, and we can find those. Okay, just some characteristics of strong acids and bases. We should know these. Okay, the equilibrium position for strong acids towards the products, for weak acids towards the reactants. Ka is going to be large for strong acids, small for weak acids. Okay, because approximately 100% of our strong acids form products, really small percent, like 1.3 or sometimes weaker than that, form our weak acids. Okay, and then the conjugate bases of strong acids are really weak, less than water, so like we don't even count them as bases, where our weak acids have strong conjugate bases. Okay, and just kind of showing, like, again, like a strong acid is strong because it forms so much hydronium. A weak acid, only a little bit forms hydronium, and lots of it just stays as that weak acid. Okay, again, I'll do all the practice questions on the next video. Okay, just so I can write them out and so you can see them. Okay, but we'll just continue with the notes. Again, percent ionization of a weak acid is the fraction of molecules, okay, that ionize compared with the initial concentration. We did this. I made a video on how to do these problems where like we are given the percentage. Okay, and so you can watch that video if you have any questions with that. Okay, two calculations involving Ka constant are common for weak acid solutions. So these are types of problems you'll get. So calculating the Ka value from measured empirical concentrations data. So like you're given the concentrations, okay, you might have to use an ice table to find the concentrations at equilibrium, and then you're just putting them into your Ka formula. Okay, or we can use our Ka value to predict the concentration of hydronium ions for an aqueous solution where the initial weak acid amount concentration is known, calculating the Ka concentrate. Okay, and so basically, again, we'll probably be using ice tables, things like that, and so just finding our concentrations. Okay, so here's the outcome that like this is what it says I have to teach you. So calculate the equilibrium constants and concentrations for homogeneous systems and Bronsted-Lowry acid bases, excluding buffers. Okay, so here's our three kind of calculations. So when the concentrations at equilibrium are known, those are the easiest ones. They give you all the concentrations, you put them into your Ka formula. Okay, when the initial concentration and one equilibrium concentration is known, so in those cases you have to find or use an ice table, solve for X, and then put in your equilibrium concentrations to find Ka. And then the last one is the equilibrium constant and one equilibrium concentration are known. Okay, and so those are the cases where you have to kind of work backwards, okay, solving for X based on your equilibrium concentration. And for those ones, often you'll need to use your rule of 1,000, okay, because yeah, like in most of those examples, you would need the quadratic equation, but that's excluded. So you may use this method when responding to an open-ended question, just meaning that like in some cases you might say, this is where I'd use the quadratic equation, but instead I'm using the rule of 1,000. Okay, all of these, when you see these sample problems in the blue, these are out of your textbook. So I'm not going to do all of these sample problems, okay, just because like they're laid out for you nicely in your textbook. Okay, this is on page 738. If you want to see me do them, just again, feel free to email me. I'm happy to do them for you. Okay, but I didn't want to just kind of do them twice when you can just look them up in your book. And so these are some more. So this is on page 739. Okay, both of these examples. I'll do all of these examples on the next video for you. Okay, and then again, this sample from page 740. Okay, and it just kind of, for this one, it allows us, we're calculating the hydronium concentration from our Ka. Okay, so it allows us to predict the acidity of any weak acid. Okay, and yeah, for this one is when you're going to use your rule of 1,000, which they do in your textbook when you're solving for it. Okay. For communication example number 3 is on page 742 of your textbook. I'll do the methanoic acid example in your next set of next video. Okay, and that's as far as we need to go kind of for your assignment 3.5. Okay, and after 3.5, we have one more assignment. Okay, and then we'll have your equilibrium unit exam next week.